Last time you said something about
You gotta speak up a little bit for this old guy.
sorry. The other day you said something about how you wouldn't be here, so that's an episode.
Oh yeah. Okay. Yes, I am not going to be here a week from today, the Friday before Labor Day weekend. So yes, so no class a week from today. So, all right. So if this is your only class on a Friday, you can leave early. So, and all right. So we had homework due last night, so it's either posted online. I didn't care if you posted it a few minutes late, right? I don't want a song and dance email about that. It's not a big deal. Or you're going to turn it in today. So the first thing I like to do is start with homework questions over section 2.1. So any of those problems in 2.1 that you worked for last night, you want me to go through? We're all good? All right. Sometimes we'll have that, and sometimes there will be. Oh, Magnus. 12. All right, so let's look at number 12 here. Given the function, so number 12. So we're given the function, and our function is f of x equals minus 16x squared plus 64x. Complete the following. And we want to complete the following for x, f of x, and 2, f of 2. For x equals 1.5, 1.9, 1.99, 1.99, and so forth. So one more 9. So I got to put in a bunch of values, right? Anytime I'm going to put in a bunch of values, what am I going to do? I'm going to build a table and then put in the x values at the end. All right, and what do we have to do here again? Find the slopes of the secant lines. And what do we know about a slope again? Slope again is what? The difference in the y's over what? The difference in the x's. So that same line formula we're going to be using a lot in this class. All right, so this is going to be then, I'm going to call this f of x minus f of 2, because we got that specific point, over what? X minus 2. All right, so let's figure out what f of 2 is real quick. And my function is up here, so let's just do f of 2 right here. Oops, sorry about that. F of 2, that's going to be minus 16 times 2 squared plus 64 times 2. 2 squared is 4. 4 times 16 is 64. So that's minus 64 plus 128, which is what? 64, right? Did I get that right? Check my arithmetic. All right. And you can do that on a calculator. I'm just pretty fast at that stuff. So now we have our secant slope to be, well, our f of x, which was what? Minus 16x squared plus 64x. And then it's minus f of 2, which is what? 64 over x minus 2. All right, Magnus and everybody else? And then what do we need to do? We need to put what? In those values. And I don't know if that will factor easily or not. I'm just going to put in the values now. So let's build a little table now. And I'm going to build my table on these little TI-34s. So let me go here. And let me get out my TI-30. And let me just reset my calculator real quick, just because sometimes I got a lot of stuff on it. Okay, so I'm going to go to my table. And first thing I'm going to do is, since I'm putting in a fraction, I like to hit my fraction button first. Numerator, denominator. And then I'm going to put in my numerator minus 16x squared plus what? 64x minus 64 and what? All divided by what? X minus 2. All right. And then I like to have it on ask, right? Or right now it's on auto. I don't know how it got on auto. Somebody must else you taught a class in there and used the calculator. So I like to go ahead and I'm going to arrow down, and I like to have it on ask because we have very specific values we want to put in, and we don't want to just build a table stepping up from 0 by ones. Hit enter again and again. All right, so our first x value, and so let me go ahead and put this here. We have our x, and we have what? The slope. So our first x value in this problem was 1.5. So let's put in 1.5 real quick. 1.5, and what is the slope of that secant line there is what? 8. Then let's put in the next one was what? 1.9. Getting a little closer to 2. And notice in that formula, we can't put in 2. Why can't we put in 2? That would cause what? Division by 0. Put in 1.9, hit enter, 8/5, and that's what? 1.7, let's see, 8/5 would be 1 3/5, so that's 1.6. And then let's see, what our next one's what? 1.99. Hit enter, and 4/25. I don't know why it gave it to me. So 4/25 is what? Not 0.08. It'd be 0.08, 8%. 16%, excuse me, 4 times 4. So we double check. Is that what you have, Brian? All right. And I should have changed my mode on my calculator to get it out of decimal form. This should get it out of decimal form. 1.999. Oh, no, it isn't still. So I got to multiply that one by 8. So that is 0.016, if I did that right in my head. Did I get that right? And I'm doing this in my head. And how do I know 8 times 125 is 1,000. And I used to teach math for elementary, so I'm really up on some of these little things. So 1.999, one more 9, hit enter. Ooh, 1 over 162.5. That one is outside my range and without a little bit of thought. 0.0010. Thanks, Tristan.
No, 1.6.
1.6? I thought it should be a 6 too, actually, literally because of the pattern there. All right. Okay. Now we could keep putting in there. What do those values look like they're approaching there, Magnus? 0. So what's our conjecture? Our conjecture here, the slopes of the secant line, our conjecture would be that the slopes, approach 0 as x approaches 2. And that's a conjecture. It's not a proof, but it's our intuition based off of those values. So that's part B there. And what is the relationship between your answer and B and the slope of the tangent line there? Well, let me draw that picture now. Here's our function. Here was 2, which just happens to be the vertex of that parabola. We were finding slopes of secant lines, like here was 1.9. And what were we doing? I got to get this back where I can point it here. What were we doing? We were making this value get closer and closer. And as this went closer and closer, what's happening? Those secant lines are approaching that tangent line. So what is the relationship between your answer and B and the slope of the tangent line? They're actually equal. And you can tell that tangent line there is horizontal, just by look. So, all right, so that takes care of number 12. And notice what that's going to be happening is, remember, we're trying to find the average rate of change, or the instantaneous rate of change. It turns out it's going to be the slope of the tangent line, and we're going to use secant lines to work up to that. All right, and then we'll be through that theory pretty fast, and we'll then be into formulas and stuff. All right, any other questions out of 2.1? All right, so now those that are turning it in on pencil and paper, I am very specific how I like it turned in. First off, you're going to fold it the long way like a hot dog bun, not like a hamburger bun. And then You want to make sure your name is clearly printed at the top. First and last name, right? You can't just write Tristan, because one, I have two Tristans, although they are spelled differently. And don't just write your first letter of your first name, because or your last name, because I alphabetize these first by your last name, so I need to know your last name, because I put them, it's easier to put in the grade book alphabetized than individually. And I have 4 classes, so I got about 100 students or so. So it really does help if you write out your full name for me, because it takes me a while. So go ahead and write out, fold them the long way, and you either turned it in on pencil and paper or electronically, it doesn't matter. Come around and collect it. All right, we'll work on the top next time, because I look at the top. That's at my bifocal level. Now I'm going to be messed up, go that, but I'll get over it, Miguel. So, very good. Anybody else turning it in old school? All right, the rest of you turning it on online. That is awesome as well. Hopefully everybody did that assignment. And then what happens is I can quickly, they ride better in my book bag this way. I quickly just put them into a little there, and I know I got all my 2200s together. All right. So we've done the announcements, and we've taken care of the homework. We have our 2.2 homework due Sunday night. And we're going to take our first 2.2 homework, have our first quiz over the 2.2 homework. So reading graphs and stuff. Okay, so last time we were in section 2.3. Let me get my notes open to that. And we were starting to look at the limit laws. Okay, we had that intuitive definition of limit saying, hey, if the function approaches the limit, you got to give me a target. You got to what? Find the exit values that would all stay within that target. So you say you want your limit's going to be this. You say I want to be within a half inch. You got to come back and what? Be able to find some interval around that a that all the function values stay in there. Now that's a nice definition, but it's what? Hard to work with when you're doing lots of complicated functions. So then what did we do? We started building up there. And so let's just start off. Our first theorem was, and this is just a repeat, if we had this type of function here, f of x equals mx plus b. What was that function again? Mx plus b, come on. What? A slope, well, it's not what type of function. It has slope in it. It's a line, right? So first we did lines. And what did we find? The limit as x approaches a of f of x. Well, what could we do? Direct substitution. We could literally just plug in that value and we get ma plus b. And this we refer to as direct substitution. When you can just plug in the value and get the limit. And we love those because those are the simple ones. All right? And so we already saw that we can do linear functions by direct substitution. Then we went up to what? Polynomials. What was a polynomial again? A polynomial was a bunch of terms, a sub n, x sub n, a sub n minus 1, x sub n minus 1, ... down to some constant. Oh, I skipped over one, but I'll put it in here. And what could we do on the limit as x approaches a of a polynomial? We can just plug in the a as well. Direct substitution. So we love polynomials, and lines are also what? Polynomials. Okay. And then we had rational functions. And rational functions were f of x equals some p of x over q of x, where p and q are polynomial functions. So remember, a rational function is just a polynomial divided by a polynomial. And then what did we have there? We had the limit as x approaches a of f of x. Well, what could we do? We could plug in the a into the polynomial, provided one thing, q of a does not equal what? 0. All right. If q of a equals 0, we have to do something else. All right, so that's kind of where we left off last time, and we had a couple other rules there. So let's warm up with a couple of problems here. Evaluate the limits. Let's go with the limit as x approaches 0, 3x to 15 minus 7x squared plus 7x plus 5. Evaluate the limit as x approaches 0. Let's go with x squared minus 9 over, not x approaches 0, but x approaches 3 of x plus 3. And let's go with the limit as x approaches minus 3 of x squared minus 9 over x plus 3. All right, so I'm going to give you a few minutes to try those three limits, and then we'll continue on finishing up this section. Two, 4, 6, 8, 10. Missing a few today, but I definitely know I have volleyball and a few others gone, so. Caleb?
I see where the first one is 3x.
15th power.
Okay, cool.
Or whatever power you want. It ain't going to matter. As you see now. You get up to powers big like that, and you're only putting in one of three numbers, 0, 1, or minus 1. In a college math class, because nobody wants to look at big numbers. I don't know if I've told you this yet, but math is so much better without numbers.
On that table, not to get away from this, but the table earlier, you were saying that you didn't know why it was showing fractions instead of decimals.
Yeah.
Is there a way to get it to show decimals?
I believe all you have to do is go to mode and change it out of pretty quick.
It's a mode there.
So you go down and you put it into fixed decimals. But I never remember to do that. And you know, I was surprised on the last one because there's a limit on the fractions that those calculators can do. And I really had the last one and would give it to a decimal. Okay, so what about the first one? You look inside that limit. What is that function right there? If you had to name what type of function this is. Polynomial. Do we love polynomials? Yes, we put in 0. Now, when you put in 0 for x, I don't care, 0 to any power is what? 0 other than 0 to the 0. That's an interesting question coming up. So we put in 0 and all the way along there, and what are we going to come up with? 5. And you don't really need to do any work on that. I'm supposed to get a new device this semester. All right, so that one would be 5. All right, tried changing batteries. There we go. Okay, so this next one. What do we have here? Well, you look in the numerator. Is that a polynomial? It is. This is a polynomial. So we have what type of function? A rational function. And then the first thing we hope is when we put in the value into the denominator, it's what? Not 0. So I put in 3 down here. 3 plus 3, is that 0? No, are we happy? Yeah, because what can we do? Direct substitution. Anytime we can do direct substitution, we are happy. So that's just what, 6. Put in 3 up here. 3 squared is what, 9? 9 minus 9 is what, class? 0. And we're allowed to divide into 0. We're just not allowed to what? Divide by 0. All right, this next one. We put in minus 3 here. Uh-oh. What's the problem? 0. All right. What happens if I put in minus 3 up there? 0. So what we have here is 0 over 0. 0 over 0 is one of those forms that pops up. It is not, does not exist. It is, oh, sometimes we've got to do more algebra. So, remember, we're only interested in as we're going into negative 3. So I think I can factor that numerator there. That numerator factors as x plus 3, x minus 3. That denominator is just x plus 3. Anybody see anything that will cancel? X plus 3's. And we can cancel that as long as x is what? Not negative 3. But remember, as we're doing our limit, we're only interested in as we're going into it. We don't care what happens right at that point. So we're allowed to cancel that. And now, what do we have in that what do we have left in that limit now? What type of function? What is that, class? Well, we could call it a line or we could call it what? A polynomial, either one. And can we do direct substitution now since it's a polynomial? Absolutely. So we put in minus 3. Minus 3 minus 3 is what? Minus 6. So what happens is when we start doing direct substitution and we start seeing things like 0 over 0, what does that say? Do some algebra. You got to do some of that algebra. Sometimes it might be factoring. Sometimes it might be rationalizing a numerator or a denominator. All those intermediate algebra skills that your high school teachers promised you you'd use again. Well, guess what? You're the select ones that got up to the level that you're going to use them again. How good does that feel? You made it. Right, Tristan? You made it. All right. So let's look at this problem. Yeah.
Missed the explanation. Why are we turn the negative 3x squared into x plus 3?
Oh, it's factoring. I just factored that numerator. X squared minus 9. It's the difference of squares. It factors as x plus 3, x minus 3. Let's back up here, Kelly. So I took this numerator. I think that's what you're asking me. And I factored it as x plus 3, x minus 3. Difference of squares. Yep, we might be a little rusty on our factoring, but we're going to pick up our factoring in this on the limit laws because we do factor there. All right, good question. Any other questions? So, and by the way, when I put in and got 0 there, that pretty much tells you that x plus 3 is a factor. All right, so let's go to this next one. Let's look at the limit. As x goes to 2, the square root of 2x cubed plus 9 plus 3x minus 1 over 4x plus 1. Okay. Is this a rational function? Yay or nay? Nay. What's the problem there? This pesky little square root. So we haven't talked about taking the root yet. So now let's go back and review our limit laws. Hang on, you're going to get whiplash real quick. Let's go back and review our limit laws from last time. Just the start of this here. And what were our limit laws again? Well, first off, we could add or subtract two functions, and limit of a sum or a difference was what? The sum or difference of the limits. So we could split a sum or difference apart. We can, pull out constants from a limit. And we can deal with what? Products. And we can deal with what? Quotients. And then we also had the power rule, but that was for what? Whole number powers. Okay. So we need another limit law because we haven't talked about radicals yet. So let's put in our 7th limit law here. This is the 7th one. I know where I would ever ask you what's the second limit law. That would be pointless, ridiculous. A few other choice adjectives come to mind, but I'm filming. So this one is called the root. And we're still going to take our n's to be out of the set 1, 2, 3, so forth. So we're still looking at what? Whole number n's. Now, if n is even, then the limit as x approaches a from the positive side of f of x to the 1 over nth power. I'll let you get this copy down and I'll talk about what we really got going on here. Probably not my favorite way I've ever seen this law written, but it's how this author writes it. This is probably my second favorite calc book to teach out of, but more of the department likes this one than my favorite. All right, so like if n is 2, then 1 over n is what? 1/2, which is really like if you think about x to the 1/2 power, we're really talking about what? The square root of what? X. So this is really roots or radicals, and this is how we represent a root instead of writing as a radical. So this could be a cube root, this could be what? A 5th root, this could be except it has to be even, so this could be a square root, a 4th root, a 6th root, and so forth. All right. All right. If n is even, and I got to bring this down, I need to write some more here. Then the limit of this will equal the limit as x approaches a from the positive side of f of x, 1 over n. What did this say? This really just said, hey, we had the root inside their limit. Now what do we have? The root what? Outside the limit. So think of this as the square roots inside there. Now we're doing the square root of what? The limit. And I'll let you get that kind of written down in your note. So we're doing even roots. Can we do any even root of any number? No, the second commandment is thou shalt not take square roots of what? Negative numbers. So what's this? This will only exist if f of x is greater than 0 for x near a with x being greater than a. And I'll let you copy that down and I'll put that into a little bit more of an English. And I might even put it in radical form. Question back there on what I've written? What's that? No, these I'll write it as a radical so you can kind of see it more. Okay, so radical, yeah.
Sorry, I'm just getting confused. What's the plus next to n or t or whatever on the x approaches?
Yeah, as x approaches a from the positive side.
Positive side.
Yep. Remember, so if I'm approaching a from the positive side, are my x values bigger than a or smaller than a? Bigger. That's what this piece says here. Okay? So what this says is, hey, if we're doing like the limit as x approaches, let's say 4 of the square root of x. All right, what this says is, hey, you can take the square root outside. So here's your radicals, Tristan. That's a radical. I may look radical, but that's a different use of radical. All right, this becomes a limit as x approaches 4 of x. Now, we're allowed to do this if this f of x is positive around 4. Well, if you think about this function, what is this function here? F of x equals what? The square root of x. What's that function look like? Right here, doesn't it? And we're allowed to do this as long as we're coming into 4. These y values are what? Bigger than 0. Are they bigger than 0? They are. All right, we can even come down here because we only have to be coming in close to it, not right at it. All right, so what is this, class? Polynomial, right? Very simple polynomial. Are we allowed direct substitution? Yeah, so this now becomes the square root of 4, which is what? 2. So we'll streamline this process along the way, but that's really what this theorem says. All right, the first part here. All right, so the second part. So that's what? If n is even. Oh, and that's the right-hand side. So then we also have, and I'll probably re-summarize this at the end here. I'll re-summarize it maybe tomorrow, or no, Monday. Just the limit as x approaches a from the negative side. So this is still the even case of the f of x to the 1 over n. So we're still talking about a radical. This is the disguised form of a radical. By the way, I used to have this cool tie-dye shirt I'd wear on radical days, but my kid took it. So you lose all your good stuff to your kids. So, all right. Well, we can also bring out that radical. And what's going to happen there as well? Well, we're going to have a few conditions. And the conditions is f of x is greater than 0 for x near a with x is less than a. So we're coming in from the negative side, So basically this says, hey, if you're doing an even root, a limit of an even root, you better make sure what's underneath that radical there is what? Positive, or at least what? Non-negative. And then you can what? Pull out that radical. All right. And that's for even. And why are even roots a little more tricky? Because thou shalt not take what? Square roots of what? Negative numbers. Can we take a cube root of negative 8? Can we do odd roots of negative numbers? Yeah. So the odd ones are going to be much simpler. Matter of fact, I didn't even write the odd ones in here. Oh. If n is odd, the limit as x approaches a of f of x 1 over n is simply the limit as x approaches a of f of x 1 over n. We can do the odd roots of negatives, we can do the odd roots of positives and 0, so the odds are no problems. Now that's heavy in notation. Mathematicians are famous for hiding concepts in notation. But the reality is, what do we have to do? Make sure when we're doing roots, if we're doing an even root, make sure what's going underneath that radical there is not approaching a negative number. If we're doing an odd root, it works just fine.
From the positive and the negative side?
From the positive and the negative side. Doesn't matter, Brian. Very good question. Give everybody a chance to get caught up. All right. Okay, you've been sitting for like 35 minutes. Why don't you just stand up and go meet somebody you haven't talked to in class, see what they're doing for the weekend, see how their week went, but get a stretch. It's too long to sit for that long. I know I'm probably the only teacher that gives you, I'm the only guy that gives a stretch during class. All right, let's get back at it now. So we're back to this problem. So let's just apply the limit laws. We'll just go old school, we'll break this out. So we know the limit of a quotient is the quotient of the limits. So this would be the limit as the numerator. Oops, I don't need parentheses around that. Over what? The limit of the denominator, provided what? Both limits exist. So if somewhere along the way this becomes does not exist, one of these, we got to back up and say, we got to maybe try something else.
We wrote down the square root x squared, I think it should be x cubed.
It should be x cubed. Thank you, Brian. I would have caught that when I was doing direct substitution because I know it's supposed to have a nice number. All right, now what do we got going on in here? We got a sum. And this is not a polynomial. Why is it not a polynomial? Because that pesky little radical there, that square root. Is this a polynomial? Yeah, can we do direct substitution on that? Yeah, as long as it's what, not 0? If we put in 2, what's 2 times 4? 8. One more makes what? 9. So we might as well take that limit. And at this stage, most of you can just put that into your head and calculate that out. I don't need to see the steps. So we'd say the bottom is what? 9. Now how about the top? The top, I'm going to rewrite that. That's a sum, so I'm going to rewrite that as a sum of the limits. Okay. Give you a chance to get caught back up again. What's inside this limit? What's inside this limit's a line, right? Direct substitution. What's inside this is this radical, right? And it's an even radical, right? Square root, that's even. So I just need to make sure when I put in 2, this is not going to a negative number, it's going to a positive. So put in 2 real quick. What do you get? 2 cubed, which is what? 8. Times 2 is 16, plus 9 more is 25. Here's your tough question of the day. Is 25 positive or negative? Positive, right? This is that f of x is going bigger, is greater than 0 as we go into 2. So what can we do on that one? We can literally bring out that square root. Here we can go ahead and do direct substitution. So when we do direct substitution in that 3x minus 1, 3 times 2 is 6, minus 1 is what? 5. So I did direct substitution there. And you don't need to show me plugging in the numbers, unless they're big numbers and you want to plug them in just so you don't lose track of them. And then let's see, let's put in 2 here. Well, we already said that was what, 25? So this becomes the square root of 25 plus 5 over 9. So that's 5 plus 5 over 9. So what is this limit? This limit is what? 10/9. And so we can pull those radicals out of a limit, but we got to make sure if it's even that it has some non-negative number in there. Okay. Questions on that example? I'll give you a chance to get caught back up. We've got a couple more examples out of this section. Okay, so let's look at our next problem. Let's let f of x equal x cubed minus 6x squared plus 8x over the square root of what? X minus 2. And let's start off by looking at some one-sided limits. What's the most interesting x value we might be interested in is what? 2, right? So let's start off with looking at the limit as x approaches 2 from the negative side of f of x. So we are approaching 2 from what? The negative side. And we're really interested in what's going on here. Now, what type of root is this? Or radical. This is a radical, right? What type of root is this? This is what? A even root, right? Square root. So, what do we have to worry about on square roots? Negatives, right? So pick out a number. We're going into 2 from the negative side. Pick out a number smaller than 2 from the negative side and see what happens when you put it in there. It's got to be close to 2, but not right at 2. All right, I'm going to pick out 1.9. Nice simple number. If I put in 1.9, 1.9 minus 2, positive or negative? Negative. Oh, so it doesn't even exist on that side of 2. So what is this one? Does not exist, since square root of x minus 2, or since x minus 2 less than 0 when x is less than 2. All right. So that limits what? Does not exist, because we can't do square roots of what? Negatives. So now, let's look at the limit as x approaches 2 from the positive side. Pick out a number bigger than 2 and plug it in. Is it positive or negative? Positive. So you feel like, oh, I'm going to get limits of positive numbers under that radical. So let's do this limit. So this is going to become the limit as x approaches 2 from the positive side of x cubed minus 6x squared plus 8x over the square root of x minus 2. And later on we will abuse the limit laws, but for now we're going to use them appropriately. What do we got going on there? A quotient. So this is going to be the limit as x approaches 2 from the positive side of the numerator plus the limit over the limit, not plus, limit as x approaches 2 from the positive side of the square root of x minus 2. All right, so look in the numerator. What's inside that limit? What type of functions inside that limit? Polynomial. Can we do direct substitution? Absolutely. We love direct substitution. And the bottom, we can't quite do direct substitution yet because of what? We got to that radical there. So this becomes, let's do the direct substitution on the top. So on the top, when we put in 2, what do we get? We get 8. 2 squared is 4, 24. 8 minus 24 is what? Negative 16. And when I put in 2 up there, is that 0? Double check my arithmetic. Is it 0? Alex, got to agree 0?
Yeah.
0 in the numerator?
Yeah.
And then down here we'd get the limit as x approaches 2 from the positive side of x minus 2 over the square root. All right, this is a line, right? So we put in 2. What's 2 minus 2? 0. Oh, and so that, what's the square root of 0? 0. What do we have here? 0 over 0. That is, try something else. See? You get to use cool words. Try something else. Plain, simple English there. All right, so we got to try something else on that one. That's going to come up later. But let's go ahead and talk about the limit as x approaches 2 of f of x. Was 2 we were going into. So what did we show on the one? Did we get one of the one-sided limits to be undefined or does not exist? We did. So remember, on a two-sided limit, both limits have to exist, and this one is does not exist since the limit as x approaches 2 from the negative side of f of x equals what? Does not exist. But this limit is still, that single-sided limit is a cliffhanger for us. We'll come back to it at a later time, not in this section. All right, now let's look at this one. Let's take the function to be x squared minus 6x plus 8 over x minus 2 to the 1/2 power. And we want to know what is the limit as x approaches 2 from the positive side of f of x. All right. Anybody see a disguised radical? The 1/2 power, right? So we have to watch out for that. So this is what? Square root of 1/2. So we already can't put in numbers, what, smaller than 2, because that would cause, what, division by 0. That's why we're only doing from, what, the positive side. All right. Now, go ahead and put 2 into the numerator for me real quick. Just do a quick direct substitution in the numerator. And what do we get in the numerator? Mark? 0. Ah, very good, Mark. 0 over 0. So this says, hey, there's probably some algebra to do. So let's factor the numerator. Let's factor this. X squared minus 6x plus 8. See if that factors for me. I'll get you started. There's an equal sign. There's the x. Factor that other piece for me. And I believe it factors as what? X minus 2, x minus 4. Double check my factoring. Ah, here's an x minus 2, here's an x minus 2. So these will cancel out, right? Well, they won't completely cancel out. The power on this is understood to be what? A 1. And what do you do when you divide? You subtract exponents, right? So what's 1 minus 1/2 is what? 1/2. So we could say, okay, this cancels, leaving behind an x minus 2 to what? The 1/2 power. Sometimes we can cancel those things out. And now what's this going to become? Well, since we're only interested as we go into 2, not right at 2, we're allowed to do this canceling. This is going to become the limit as x approaches 2 from the positive side of x. And I'm going to go ahead and write that the square root of x minus 2 times x minus 4. All right. Now, x and x minus 4 are multiplied together as a polynomial. So let's pull them out there and make that limit as x approaches 2 from the positive side of x times x minus 4. And then we'll split off that second piece, the limit as x approaches 2 from the positive side of the square root of x minus 2. Okay, this is a polynomial. It's just not multiplied out. We'll do it in our head. This is a radical. even radical. So we got to make sure we're putting in coming in on the positive side. So pick a number bigger than 2, close to 2, and put it in there. Decide if it's positive or negative. Let's see. Miguel, what number did you pick out? 1.9? Oh, we got to be bigger than 2. 2.1. That was a better choice. 2.1 minus 2. Positive or negative, Miguel? Positive. So we're taking square roots of positives. Are we allowed to do square roots of positives? Yeah. So technically right now our next step would be this. And I could have multiplied that out right now. Our next step would be pulling out that radical. Okay, so let's just do this piece here. Now this is a constant, or this is a linear function, right? Let's put in 2. What's 2 minus 2? 0. And that limits 0. What's the square root of 0? 0. And this is not 0. What's anything times 0? 0. Although we want to put that in, that's 2 times minus 2, so that's minus 4 times 0, which is still what? 0. Okay. Now, we have other functions that are not as nice to play with. So let's take a look at this function here. Let's take a look at the following function. F of x equals x squared sine of 1 over x. What x value can't we plug into this function, class? 0. Thou shalt not divide by 0. So what would be the interesting question then? What is the limit as x approaches 0 of x squared sine 1 over x? Well, there's a little bit of a problem. First off, this is a trig function. This is our first trig function we've talked about limits of. This is a polynomial, so you have 0 times something, but sometimes 0 times something isn't 0. And we'll study that quite a bit. So we kind of got to have some tools around here. We probably think it's going to 0, but we need a little bit of a tool. All right. And we need what's called the squeeze theorem. Or sometimes you'll hear me call it sandwich theorem because it has 2 different names depending on which textbook you use. All right. If f, g, and h are functions such that, so we got 3 functions floating around, f, g, and h. F of x is less than or equal to g of x is less than or equal to h of x for all x values near a except possibly at a. Give you a chance to get that written down. Okay, so we have 3 functions. F's the smaller one, G's the middle one, H is the bigger one. Okay. If the limit as x approaches a of f of x equals the limit as x approaches a of h of x, and those equal some number L. So the small function goes to L, the big function goes to L as we go to A. So they're both going to L. What do you suppose the middle function has to go to? L as well, because it's squeezed in between them. And that's what the squeeze theorem says. Then the limit as x approaches a of g of x equals L. So if you can find two functions that one's below and one's above and they all go to the same spot, the middle one has to go there as well. Give you a chance to get caught up, and then we'll do a couple of these. And these are really going to be the ones that help us get some trig identities established. All right, so our first problem is this. We're going to show the limit as x approaches 0 of x squared times sine of 1 over x equals 0. This is what we're going to show. All right. Well, let's start with the trig function sine of 1 over x. From your trig days, anybody remember what is the range of the trig function? What value, what's the smallest the trig, what the sine function could be? What's the biggest the sine function could be? 1 and -1. Remember, and I didn't teach you guys trig, other than a couple of you. I think going around that Ferris wheel, the y's can go from -1 to 1. So it doesn't matter about the 1 over x. Yep.
Are we going to need like a unit circle for this move along? Or?
Not too much.
Okay.
But we need this identity right here. We know sine's always between -1 and 1. All right, so now we have this bounded, but we got to get x squared involved. Is x squared positive or negative? Well, it's positive, right, generally. We remember, if you multiply inequalities by negatives, you got to flip them over. But generally, x squared is what? Greater than or equal to 0. So we can multiply all three sides by x squared. So now we have minus x squared is less than or equal to x squared. Sine of 1 over x is less than or equal to x squared. So now we have this function here that we're trying to find, and we have it what? Stuck between two functions. This is the smaller one, this is the bigger one. Now where is x going to? X is going to 0. Is this a polynomial? It is, right? Minus x squared polynomial. Are we allowed to do direct substitution? We are. So here's where we just say, oh, this goes to 0, right? And does x squared also go to 0? It does. So where must the middle go? Well, if that's 0 and that's 0, and they're all less than or equals, this is also what? 0. So therefore, the limit as x approaches 0 of x squared sine of 1 over x equals 0 by the squeeze theorem. All right. So with our sines and cosines, we often will squeeze them. Okay, give you a chance to get that one caught up. And now, let's look at our next one. The next one we want to look at is f of x equals sine x. And we're really interested in what is the limit as x approaches 0 of f of x. Might as well write sine x there. Okay, so we're going to squeeze our sine between two functions we know a lot about. All right, so first off, now remember, we're really only interested in as we get close to 0. So we don't have to worry too far. We're going to stay close to 0. And let me go ahead and get out GeoGebra here. I'll put it over on the far board here. And let me just go ahead and graph a couple of functions here. And I'm going to graph y equals the absolute value of x. And from previous days, the absolute value of x is what? A v, right? Opening up. And then I'm going to graph y equals minus that absolute value of x. And then I'm going to put in y equals sine x. Okay. And I guess I'm going to move it over this board too so I have something to point at. So, oops, too far. So here's the absolute value of x. Here's minus the absolute value of x. Are those two functions bounding sine x? And where do the absolute values x go to? They go to 0, right? And then where does the sine x have to go to? 0 as well. So if we look, sine x is always going to be between minus the absolute value of x and the absolute value of x. Well, if you put in 0, this goes to 0, this goes to 0. So where does the limit as x approach 0 of sine x go to? It also goes to 0. All right, so we can squeeze some of these in. All right, so let's take an example of one more here. The limit as x approaches 0 of cosine of x. Oops, sorry. If I ever forget to turn it back over, please let me know. All right. Now, your gut instinct says it probably should be 1, right? Because cosine of 0 is what? 1. So let's see if we can bound this function between a couple of things. And the two functions we're going to bound these between, and this would be more by discovery. We know cosine is strictly less than 1 always. And on the other side, we're going to look at 1 minus the absolute value of x. And let me get these graphed here. So I'm going to first I'm going to graph y equals 1, which is a nice horizontal constant. And then I'm going to graph y equals, and what was it, 1 minus the absolute value of x. And, oops, you can see them over there. And you see now what's my third function? I'm going to squeeze it in. And I'm going to squeeze in cosine. And I'm going to narrow it down. We want to be close to what? 0. So I'm going to go ahead and say, I'm just going to narrow it down. I'm only going to graph the cosine from negative 0.5 less than or equal x less than or equal 0.5. So I'm going to graph it around minus 1/2 to 1/2. And then I'm going to graph cosine of x. And it's hard to see there. Let me zoom in. But right around there, move this back over, right around there, here's our cosine graph. I only graphed a little piece of it. Is it bounded between those two functions? It is, right? It's in between them. Where's this function going to? It's going to 1. Where's this function going to? It's also going to 1. So where must the cosine value be going to? 1 as well by the squeeze theorem. So now that gives us the limit of cosine of x equals 1. All right. And so those are a couple of nice values to know. And they match up with your gut instinct too. Because we knew sine of 0 is what? 0. And we knew cosine of 0 was what? 1. All right. Got just enough time. Let's look at this one. Limit as x approaches 0 of sine squared x 1 minus cosine x. So first thing I always do is mental direct substitution. So put in 0 in the numerator and put in 0 in the denominator. Just mentally do a little side work on the scratch there. And just put in x equals 0 in the numerator and the denominator and see what you come up with. So when we put in 0, sine of 0 is what? 0. 0 squared is what? 0. Cosine of 0 is what? 1. And 1 minus 1 is what? 0. So what form do we have here? 0 over 0, which says, hey, you got to do some algebra. Okay, we got sine squared up there. Anybody think of another way of writing sine squared? We got cosine down in the denominator. Sine squared is what? 1 minus cosine squared, right? So I could use the fact that sine squared x is 1 minus cosine squared x, that Pythagorean identity. Cosine squared x plus sine squared x, what? Equals 1. So let's substitute that in. This becomes the limit as x approaches 0 of 1 minus cosine squared x over 1 minus cosine x. Ooh, is this the difference of squares? It is, right? And the difference of squares, what? Factors. So let's factor that numerator. That's going to be the limit as x approaches 0 of 1 plus cosine x, 1 minus cosine x, over 1 minus cosine x. Now, does anybody see things that'll cancel? Yeah, and that's really removing the 0 over 0 part. And now what do we have? We have the limit as x approaches 0 of 1 plus cosine x. And we just saw we could do the limit of cosine. What's 1? Is that a constant? It is, right? What's the limit of a constant? The constant. So that's going to be 1, and that's going to be cosine of 0. And what's cosine of 0? 1, so what's that limit? 2. So that 0 over 0 form, we refer to that 0 over 0, we refer to that as an indeterminate form. Indeterminate means you don't know what it could be. It could be undefined, it could be 2. It could be lots of different things. It's a form that says, hey, we got to do something else. All right, just enough time for one more problem. Let's take a piecewise defined function. Let's let g of x be 5x minus 5 if x is less than 4, and the square root of 6x plus 1 if x is greater than or equal to 4. And what's the limit we are interested in? We're interested in the limit as x approaches 4 of g of x. Okay, give me a second to get caught up. What's the problem with 4? It's right on the dividing line of what? Our function rules. So what do you suppose we're going to have to do here, class? One-sided limits, right? Yeah, we can't do two-sided limits because one has this rule and one has this rule. So we're going to do two one-sided limits and then see if they agree. So let's first look at the limit as x approaches 4 from the negative side of g of x. Well, that's going to be the limit as x approaches 4 from the negative side. So if I'm approaching 4 from the negative side, I'm what? Smaller than 4. If I'm smaller than 4, I'm what? Up here, right? So I'm at this rule, 5x minus 5. Ooh, do we like that? Yeah, that's a polynomial. Direct substitution. 5 times 4 minus 5 is what? 20 minus 5, 15. Okay? So sometimes we got to do the one-sided limits to get to the two-sided limits. Now let's look at the limit as x approaches 4 from the positive side of g of x. Well, what's there? I'm bigger than 4, so I'm going in on this rule. What do we have going on there? We have a radical, right? A square root. So what do we need to know? We need to make sure that what's underneath here is not going negative. If you put in 4, is that going to be positive? Clearly. We don't even need to crank it out. So this really becomes the square root of the limit as x approaches 4 from the positive side of this. Putting it in 4, 6 times 4 is 24, plus 1 is 25, so that becomes the square root of 25, which is 5. All right. Does 5 equal 15? No. So the limits are going what? Different spots. Since they're not equal, what do we conclude on this one? Does not exist since the one-sided limits are not equal. So, all right. So that concludes section 2.3. And so we'll call it a day there. 2.4. Next thing we do in 2.4 is we, instead of going into a finite value like x equals 2, we'll now let x go off to infinity, and we'll look at what happens when our function goes off to infinity. So thanks for making it on a Friday. You got some homework due Sunday night. I believe it's 2.3. And then we'll have our quiz on 2.2 on Tuesday. So have a good weekend.
You too.